Let's review theoretical, actual, and percent yield. The amount of product we get if the reaction is perfect is called the theoretical yield. It is found by calculation. If we actually do the reaction and measure the actual yield, we will find that this amount is typically less than the theoretical yield. And at the bottom of the screen here, the percent yield is simply the actual yield that we get divided by the theoretical amount that we should have gotten if we were perfect. It's very analogous to percentage on a test. It's the number of points you actually get divided by the number of points that, in theory, you could have gotten had you been perfect. So let's try a problem. Automobile airbags inflate with nitrogen via the decomposition of sodium azide. And there's the chemical reaction. Actually, I think this is only the first chemical reaction. I think there are one or more others that take care of this sodium product that could be problematic if it weren't reacted into something a little more innocuous. In any case, at STP and a percent yield of 85%, what mass of sodium azide is needed to yield 74 liters of nitrogen? We know we're going to have to do some stoichiometry here, so let's get out our stoichiometry island diagram. We can tell from the wording of the question, it says, what mass of sodium azide is needed? So clearly, the right side of this island diagram is going to be representing sodium azide, and we're given an amount of nitrogen. So that would be the 4 islands on the left. Furthermore, we're given liters of nitrogen, and we want to get to mass of sodium azide. So hopefully you can see that in this problem at some point we're probably going to have a stoichiometry calculation that has 3 conversion factors because we're crossing 3 bridges. Okay, but in this problem we have the percent yield to deal with. So let's write out the percent yield equation. Percent yield is equal to the actual over the theoretical. Notice I've taken out the 100%. So obviously the 85% is going to go on the left side of this equation as 0.85. Now, does this 74 liters of nitrogen, does that sound, from the context of this question, does that 74 liters of nitrogen sound like an actual amount that we have to have, or a theoretical amount? Let's read the question again. What mass of sodium azide is needed to yield 74 liters of nitrogen? That 74 liters is an actual amount. We have to have that amount. If we don't get that amount, the airbag isn't going to inflate fully, and that could be dangerous. Apparently, we're just going to have to assume in this problem, let's say that we're a car company. We've done test after test after test after test, and the percent yield is very nearly 85% every time, for whatever reason. Okay, well, we need to make sure that we put the right amount of sodium azide in there so that we get our 74 liters of nitrogen. That will inflate the airbag fully, but not too much. So what we need to do is calculate the theoretical amount of nitrogen that we would get if the reaction were perfect, knowing in advance that we're only 85% perfect. Let me say that again. We need to calculate the theoretical amount of nitrogen that we should get if the reaction is perfect, knowing in advance, because we've done test after test, that we're only going to get 85% of that theoretical amount. But we still have to put in enough sodium azide so that we get that 74 liters with only an 85% yield. Actually, at this point, pretty much all of the thinking of the problem is done, because from here it's simply a matter of doing our 3-step stoichiometry calculation. 87.1 liters of nitrogen, 3 converts. The first one converts liters of nitrogen at STP into moles of nitrogen. The units cancel. like that. Now we're going to cross the middle bridge using the coefficients in the balanced equation. And those coefficients are 2 moles of sodium azide for every 3 moles of nitrogen. Notice how the moles of nitrogen cancel. And now we need to calculate mass of sodium azide. We need to calculate the molar mass, that is. Check it out from the periodic table. Sodium, Na, has a molar mass of 23. Nitrogen has a mass of 14. So 3 14s plus a 23 give you 65. The moles of sodium azide cancel. We type that into our calculator. 87.1 divided by 22.4 times 2 divided by 3 times 65. Rounded to two significant figures because both of the quantities that we were given had to 170 grams. Now, will all of the 170 grams here react? And the answer is no. Only 85% of them will react. And when 85% of these sodium azide formula units react, we are going to hit our 74 liters just like we want.